Welcome to NPTEL online certification courses on characterization of polymers, elastomers and composites. Today we are in week 8, lecture number 3. The name of the module is Thermal Analysis Techniques and Applications in Polymer, Elastomers and Composites. The concept covered today will be a basics on dynamic mechanical analysis. Even though I talked about in class number 2.3 bit about the viscoelasticity and in different modes of analysis in DMA what we can do. But today again we will have a very quick recap on viscoelasticity, then we define resilience, and resilience is a more pertinent term when you talk about a rubber. Okay. So, we will try to understand what is resilience and how does DMA work first of all. Okay. The common geometries that is practiced in DMA, response to classical extremes and oscillatory tests, storage modulus, loss modulus, tan delta, those are the basic parameters that you derive from the dynamic mechanical analysis. A typical DMA plot measuring Tg by DMA, okay, and where exactly you have to choose, since you have 3 parameter storage modulus, loss modulus, tan delta. So, how to choose the correct Tg, and effects on cross-linking of the matrix. If matrix gets more and more cross-linked, how it is going to affect the Tg determination by DMA. The effect of temperature on viscoelasticity in general, bit on case studies and mostly on field system and all, and then a few standards related to that. Then coming back to viscoelasticity, actually as the term says, as I mentioned earlier also, viscoelastic, in one hand it is liquid like, other hand it is the solid like. Okay. That is what it means by viscoelasticity. Okay. So, in a consequence of that you get 2 properties parallelly, one is the viscosity on one hand, another is elasticity on the other hand. So, when a load is applied to a polymer sample in a time dependent manner, we need to consider not only the strength. Okay. Strength is a very transient experiment where we do not take time into consideration at all in most cases, but to which extent the input energy is dissipated or how much you retrieve, and that is what actually viscoelastic experiment you do. So, in general, I mean we say for a pure solid you have a modulus which is stress by strain. Here it is you have to redefine modulus is a function of time, and it has 2 components clearly. One is one which you can retrieve, and that is in dynamic analysis like E prime, and E double prime which one you never get it. So, how it happens to understand very clearly, very elementary model you can consider. Okay. It is a combination of a spring and a dashpot. Spring represents a pure solid character, and a dashpot you just think about, it is a Newtonian fluid like. Okay. Dashpot is nothing but a piston which is moving up and down on a viscous liquid. Okay. So, it obeys the Newton's law in general. So, now based on okay, obviously if you have 2 component, it can be either parallel or it can be serial combination. Okay. So, you see the first one from here is actually serial combination. So, suppose this is actually restricted movement, you put a load, suppose we assume the movement is allowed in this direction. Okay. So, that way all this load you are putting it or all the deformation you are making it on, it should be distributed to both the elements. Okay. And similarly, so if you have a parallel combinations. Okay. Parallel means here they are little bit free, not dependent, but here is a restriction. I mean in these 2 are parallelly, that means this movement is highly dependent on this movement, and that is what is generally known as, the first one is Maxwell model and second one is Kelvin Voigt model. Okay. So, this gives you both the models very elementary depiction of viscoelasticity and its consequence on dynamic properties, static properties, and even the transient properties. I will redefine what is transient viscoelastic property means. So, let us quickly look into the essence of resilience. Suppose if I give you 3 balls. Okay. So, you try to judge. So, at first instance how you judge it? you try to drop it from certain height, say h0, okay, and then let it bounce, okay, and then it bounce back. So, it will recover some height certainly, as this cartoon saying that you are dropping from here, and then after that it actually recovers some. So, classically, I mean what I told earlier, one part which is recoverable fully. So, you can consider it at E prime, and which one is not recovered. I mean, if you consider the potential energy term, E equals to mgh, okay, we are not considering any kinetic energy into that, okay, just from the rest we are dropping the ball. So, essentially if I try to see the how much height it actually recovered, and what was the initial height. So, h by h, so h by h0, if you do percentage calculation, that gives you a rough estimation of what is the resilience, that means how much it retrieves basically. Okay. So, obviously from rubber to rubber, this h by h0 ratio, which otherwise I defined as resilience, okay, multiplied by 100 of course, which will be percentage resilience, will vary. Okay. It will not only vary with the polymer to polymer, it will vary as a function of temperature as well. If you look at in this example, this is 100 into h by h0. If you plot it for cis polyisoprene, okay, cis polyisobutylene and polychloroprene, 3 rubbers, okay, and of course a plastic considered here PMMA, just for see the discrimination, I mean in properties in terms of. So, generally polyisobutylene is called damping type of rubber, it is a butyl analog. Okay. So, if you consider a room temperature, fairly enough, if you just draw a line here, you can see that this h by h ratio is obviously different. I mean of course, this point is same at that particular temperature, I mean, but mostly they are different at different temperature, it is poised. Okay. So, you can see the butyl rubber has obviously a low damping or low recovery, okay, as compared to polyisoprene and polychloroprene rubber. But of course, so if you look at the trends of the curves with respect to the rubbers, you see butyl is going upturn. So, if you increase the temperature, there is every chance that it will cross somewhere number 1, which is polyisoprene, which is considered to be one of the most resilient rubber in general. Also, you can see at certain temperature you see the minimum, okay. Those are of course corresponding to Tg, the glass transition, and of course, I mean lower than this Tg also you see a differential behavior. PMM, which is a plastic on the other hand, okay. So you can see it shows you initially it was h by h was perfect, it was recovering well, but again you see it has a near about the Tg, it has a minimum recovery, and afterwards again it starts recovering. So, this is how you do it. So, but of course, so just measuring with the ball dropping experiment will not give you the every clue, the exact form of E prime, exact form of E double prime. Just to give you a quick recap to understand the essence of viscoelasticity, as I mentioned, E as a function of time. Of course, I am talking about LVR, linear viscoelastic regime or linear viscoelasticity term. So, E t, which is a modulus, equals to sigma t by epsilon t. So, very obviously, as I mentioned it to you, you can run the experiment, okay, in 2 ways. One is the transient way. Transient way means quickly out of these 2 parameters, sigma or epsilon, you try to make it one instantaneous. That means at time t equals to 0, you make it time independent. So, what you do is, say for instance, if I do the experiment, if I try to monitor sigma t when I am putting epsilon 0, that means I am making epsilon time independent. Okay. That is what essentially means for stress relaxation experiment. And in exactly a replica of that other way around, okay, if you make stress as sigma 0 instantaneous, time t equals to 0, you apply all stress and monitor strain as a function of time, and that is what is the creep experimentation. Okay. But one of the most straightforward and in direct experimentation is just try to vary sigma as a function of time, okay, and try to see what is the response epsilon as a function of time. So, if you just quickly take the ratio sigma t by epsilon t, okay, and that you call it a composite modulus, and that actually is composed of E prime and I E double prime. So, that gives you more of a direct relationship. Not only that, in this instance you can vary the frequency very easily, you can vary the temperature very easily, you can vary the amplitude part of it, that means deformation part of it. So, you can do the experiment not only in the linear, also of course in the nonlinear region. But one of the drawback of doing dynamic mechanical properties, most of the instruments, to make it to a very high frequency region. High frequency means if I try to see the glassy attributes at room temperature. So, that may amount to 10 to the power 5 hertz, 10 to the power 6 hertz. That experimentally to date is not possible, because lot of associated inertia part, noise part will be associated with. So, of course, there are some high frequency DMA where you can go all the way up to 10 to the power 4 hertz. Rest frequency access you only can do with the help of time temperature superposition principle that I talked about earlier. But nonetheless, let us quickly try to see what we can do in dynamic mechanical analysis. In industries, engineers do not evaluate dynamic properties of polymer by bouncing rubber balls. That I resilience test elementary. It is a very elementary test. Of course, in resilience there are much precise test also, which is a beam type of cantilever type of a deflection. I am not going into that details actually. So, let us focus on dynamic mechanical analysis. So, dynamic elasticity as a function of temperature and frequency. Of course, when I talk about frequency, as I mentioned it to you, also it amounts to function of time as well. Only thing is that frequency and time they bear the inverse relationship. You can write F equals to 1 by T. So, when I utter frequency, you at the same time you try to understand its time as well. So, over the span of temperature and frequency, you are trying to understand its behavior grossly. And of course, so you apply the deformation. See, suppose if I apply a dynamic strain, epsilon equals to epsilon 0 sin omega t. So, this epsilon 0 is the amplitude. Many a times it's called double strain amplitude also. Because once you are trying to understand in sinusoidal way, in one cycle you are stretching a sample. You are stretching a sample, and other cycle you are trying to compress it. So, this amplitude, total amplitude, sometimes you call it 2 epsilon 0 for convenience, but epsilon 0 if it is single strain amplitude is of course epsilon 0 by 2. So, of course, so if I just try to see the behavior in again sigma versus epsilon. So, I apply certain static strain, say for example, somewhere I am here, and here I am doing the dynamic experiment. So, if I do not do, say for example, if I take a sample straight away without applying any pre-strain, I try to do one cycle, it will be of course tensile mode is stretching, other cycle it will be buckling. So, of course, so realistically we do experiment applying some static strain into the system. I will come back when I will talk about the modes in more detailed manner. But of course, by now you must know the LVR. Why I am emphasizing LVR? So far up to the LVR, our linear viscoelastic limits is valid. That means, your modulus is only function of time. But if I cross the LVR region, what will happen? We add complication, then this E not only become a function of time, it also become a function of strain as well. So, that is what is called nonlinear viscoelasticity. Let us not go into that complication right at this stage. So, DMA can be described. For the time being, let us try to understand it. Only for the simplicity, I showed you that the oscillatory deformation or stress is sinusoidal. It can be any periodic type of a force or strain in general. So, DMA can be described for the time being as applying oscillatory force to a sample and analyzing the material's behavior. So, ultimately grossly I am calculating, just taking the ratio stress and strain dynamically, what is the modulus, and I am coming into the details of it in a short while. Before that, let us try to do what is the anatomy of a DMA machine in general look like. Of course, depending on sometimes the DMA machine has stress control, strain control, its precision, everything is another thing, but just from a layman's point of view, what it is there. There is a force motor coil here with the magnet, and there is a temperature enclosure, where you actually sweep the temperature, and then you have a LVDT here. Okay. So, LVDT what it does actually, it actually measures the strain part of it, okay, and force part of it, monitor the other side of that, and there is a interchangeable measuring system. Actually, this is where you put your sample, and it's a furnace basically. So, to consider the constant input or output functions. Okay. Sine wave current is added to the force coil. So, that is how you generate the deformation of stress that way. Okay. So, then it's the LVDT, which is the sine wave voltage function compared with the sine wave force, and then amplitude of LVDT is related to storage modulus E prime via the spring constant K, and the phase lag delta, I am coming there. What is phase lag? Okay, is related to E double prime part of it, and that you consider as a damping part. I mean, of course, on the storage, another is the loss. Okay, and essentially, if you take the loss to storage, that gives you rough estimation of fraction of it, what it is lost actually. So, now there is no universal grip. Depending on the sample, you have to really pick choose one grip or the other. Okay. So, essentially what you have a particular grip, one part is coming out, which actually can dance with a sinusoidal form of it. Okay. So, now depending on your fixture, you try to put the sample. Say for example, out here, if you have a rigid film, okay, there all the way you go for a single cantilever mode. So, you fix that fixture out here, and then you try to do from the other end cantilever bending basically as a single cantilever. If you have, depending on how much thickness of that film is, how much is the bending modulus. Okay. Of course, if you consider dual cantilever mode, one of the drawback immediately come, if your force is low, from the both ends there is error. Wherever you have a grip, there is an error. So, you are actually applying the deformation from the midpoint of it. So, it is a dual cantilever. Okay. It can be 3-point bending also. I mean, it is a hard composite material, you can go for 3-point bending. Tension is normally practiced the sample which will not undergo creep, because remember one thing, you are applying a tension. If sample relaxes, it undergoes creeps, then the next cycle it will be different. So, you will not be able to do it. In other way, if there is certain transition in the polymer, okay, after the softening point they try to creep. So, you cannot do it. Once your sample is crosslinking recoverable within the small amplitude of deformation, then we consider there is no this part of it, I mean creep part of it. Okay. So, rubber samples, vulcanized rubber sample are normally practiced in the tension mode. Of course, tension other part is compression, but you can do it all the way. You compress it more, apply some static compression, and then on top of that 10% dynamic compression you do. So, it is all the way through in the compression mode. And for a tacky sample, say for example, okay, liquid like sample, okay, you try to do in a shear mode. So, all these modes are specific to the sample you would like to analyze. But one thing, let me clarify here at this stage, while doing the experiment practically, you have to make sure when you grip it, there should be a torque or range which will give you equivalent force to cover it, otherwise sample may undergo deformation. And not only that, you tighten the sample at certain temperature. If you increase the temperature, it may try to loosen up. So, you have make sure that at lower temperature you do enough tightening, and when I mean that, when I am putting a sample in a tension, if it is a not 90 degree, what will happen? It will have the other components of it. So, your calculation will be erroneous. So, while putting the sample in the sample rig is very important. First of all, to choose what particular mode of analysis is suitable for your sample, number one, and second thing is that you have to place it properly. Okay. Otherwise, there will be error, and you have to tighten it properly. Okay. Particularly at the lower temperature, if you do not tightening properly, at high temperature there are every chance that there will be loosen up, and you will have some false data, the noise full of noises. So, once again to repeat, if you have a very thin film, okay, and that has a certain rigidity, you go for a single cantilever mode. In general, for a film samples, okay, intermediate sort of a rigidity, go for a dual cantilever mode. A beam, say for example, which has like composite material, go for 3-point bending mode. In a vulcanized rubber sample, the first thing you should choose like a tension mode or compression mode, okay. And then shear mode is obvious for the adhesive samples or low modulus samples, you go for shear mode. So, but essentially your component shaft is giving this type of a deformation. It's all the sample ridges, sample holder that makes it in different mode of deformation, okay. So, as simple as it is. Let us quickly understand that what is tangential delta, okay. As I mentioned it to you, in oscillatory test in particular, there are two component, two part of it, stress and strain, okay. So, suppose if I apply a deformation, okay, as a that's applied on the sample, okay, and then I get a response of it, okay. Then this response obviously will have two parts. One component will be in phase with the initial deformation and another component will be out of phase, okay. So, depending on that you may figure out deformation and response, there is a phase lag, and that is defined by tangent delta, I mean that delta part of it, okay. And this delta part plays very significant role while determining how much is your storage, how much is your loss. I am coming there quickly. See, suppose if here for more simplification of it, if it is a Hookean solid, purely Hookean solid, you apply stress and you get the strain response, okay. See this, wherever you have a maxima here in the same angle, this angle, this part, you see the same angle you have this thing. So, it is actually superimposes, okay, because reason is that what Hooke's law says, there is no time dependency, equals to modulus equals to sigma by t, as simple as it is, okay. So, it is just multiplicative of that. If you take sigma by epsilon, I am sorry, sigma by epsilon. So, that way you get it that way. But when you consider a Newtonian fluid, you remember you have a time dependent factor d epsilon by dt. If you just recall Newton's law equals to it's proportional to, actually, I mean that way you get it the response, okay. Or other way around, sigma equals to, I am sorry here, sigma, please get sigma equals to epsilon into d epsilon dt. So, you have a first differential part of it, okay. So, that way if you take a sine function, if you do the differentiation, so automatically sine goes to cosine. So, you have a 90 degree out of phase stress and strain, okay. Now, if you have a combination of that, okay, like I mentioned Maxwell or Voigt model, then you have as a consequence of that, at certain angle you will get it, because it is a viscoelastic. I mean that is what delta determines how much elastic it is, how much viscosity is, okay. So, that way delta plays very important role, okay. So, that is what in a real polymer, the delta is not exactly 90 degree, 90 degree is for out of phase is for liquids, it will be somewhere 0 to 90 degree. So, if it is more, obviously it is a more liquid like behavior, liquidous behavior. If it is less, it is a more solidus behavior, okay. And generally speaking, when I talk about at high temperature responses, this delta is smaller. If you go to a low temperature response, go to high temperature response, it becomes very liquidous. So, it becomes more of like delta is more close to 90 degree. In that essence, one thing I will clarify, particularly for a dynamic experiment, DMA is no different for oscillatory rheometer. Only thing is that its sensitivity as well as its temperature regimes of interest, okay. So, when I talk about a I try to see it from the solid perspective, as I mentioned, modulus is the more pertinent one. So, E equals to, as I mentioned, I mean, and dynamically it has two components, one is a real component, another is the imaginary component. Similarly, show the, if I consider it as a liquid, it has a viscosity. So, I will put star here, okay. This is because it is a complex number. So, viscosity anyway it will have two components, is eta double prime minus eta prime into I eta double prime, okay. So, now which one is related to which, okay. This eta prime is related to E double prime, divided by omega. If you just consider a simple Maxwell model, I am not going into that direct derivation of it. And similarly, show you get eta double prime equals to E prime by omega. So, it is up to you whether you are trying to talk about the dynamic mechanical properties or viscoelastic properties. More of in that essence, modulus is more pertinent parameter there. When I talk about the oscillatory rheology, okay, of course, at higher temperature it is more viscous nature. I try to represent it in a viscosity and that to real and imaginary component of it. Okay. So, that is how it is defined. So, to be very precise, let us redefine. Okay. Your modulus, when it is time independent, is stress by strain. Okay. No need to define it further. So, storage modulus is stress by strain, but one factor is coming, there is a cos delta component of it. Okay. And then your loss modulus is a sin delta multiplied by sin delta. Obviously, if I take the ratio, tangent delta becomes E double prime by E prime. So, these are the three major parameters across which we will try to monitor the viscoelasticity of the polymers in the span of temperature and frequency. In essence, that is what is being performed in a dynamic mechanical analysis. So, that is what, if you try to see the modulus, let us try to consider my thing as a viscoelastic solid. So, in that case, the composite modulus is a ratio, and when we try to have two components of it, I have a loss component in one hand, other hand you have a storage component, and what you get E prime is a that is what in general a complex number notation looks like. And this angle is essentially is the phase lag part of it. So, that is how you can understand it. Now, let us try to see entire time, temperature or frequency. As I mentioned it to you, temperature, time and frequency in Bias inverse relationship. So, if in the time frame this is the response across, okay, obviously frequency span it is going to be just replica of it. I already talked about the modulus. If I plot it here, or log modulus to just capture the decades, okay, glassy to all the way to liquidus thing. If I do it in terms of frequency, it is just going to be reverse. Otherwise, temperature and time they will show you the similar relation. So, now if I try to see storage and loss modulus, how they go about across this whole temperature or time window, okay, you will see at the glassy state, as I mentioned it to you, it is all motions as arrested. So, it recovers, okay, its storage is more, but subsequently at the glass transition they will take over, one will take over the other, and there is a one crossover. Okay. Then loss tries to dominate. Okay. So, this left side regime is a very hard and rigid solid, almost like a time independent way it's behaving, but time dependency comes here. In the transition zone, beginning, onset and completion of it, you see two crosses over. So, one loss dominates, and then it subdues, and then tries to again catch up at the region when the rubbery plateau ends basically, and then essentially it becomes more liquid like behavior. Okay. And then of course, if you have a nano composite reinforcement, of course, for your information, here also you can get another plateau also. It is one plateau here, you can see a small plateau here before it becomes a pure liquid like behavior. Okay. It is called terminal plateau also. I am not going into that complication currently. Okay. It happens with the viscoelastic liquid. So, it was a viscoelastic solid here, and I will consider it in the terminal region, basically it is a viscoelastic liquid. So, rheology is more pertinent here, the term viscosity is more pertinent here, more prominent here. Okay. So, it is a more viscous than elastic. Here in this regime, it is a more elastic than viscous. In between, of course, it depends on what regime you are considering. Okay. So, that is how your gross DMA data can be interpreted. Okay. So, that is what you see initially the glassy zone, okay, then glass transition zone, and then you have a plateau zone and terminal zone. Terminal plateau I did not talk, let us not consider it here. Okay. So, all these changes is happening because of the small movements and their length scale of the movements. Okay. Initial transition, in the first transition, glass to leather transition, then going to the rubbery plateau, okay, it amounts to the crankshaft motion, onset of crankshaft motion I mentioned in the very beginning. Okay. And then in the rubbery plateau, what happens, it does not really matter whether there are 20 or 40 such segments giving you a cooperative movement. Okay. This cooperative movement will be all throughout the chains, and modulus remains almost constant there. So, storage becomes constant, and it tries to dominate the loss modulus. Loss modulus will be lower there. But at certain point of time, this movement is so rapid across the chain, they will try to go past each other, slip past. It flows basically, and then again loss tries to dominate. Every depiction is given here, out here, and you will be given that particular part subsequently. So now, so far as glass transition is concerned, I said that it can be captured well, from DSC. Okay, but many cases, I mean, capturing many transition, not only glass transition, beta transition, gamma transition, alpha transitions is more sensitive than DSC. Okay? Although I will not say it is absolute. Absolute determination of TG is dialectrometric experiments. Okay? As I mentioned, it can detect secondary transition. Secondary transition may be associated with small change in enthalpy that you may not, if your DSC is not so accurate, so precise, you may not, it may ignore it. Okay? But TMA will be able to, that will giving rise to some certain amount of change in modulus basically. Okay? It measures mechanical response also. As you can see, it's a dynamic experiment. If I make the frequency tending to 0, the modulus what I am going to get is exactly equal to the Young's modulus. Okay. So, you can actually interpolate it to the mechanical responses. Of course, remember one thing, we are doing at a very small deformation. Okay. And many types of clamps, I mean it does not really matter, I mean what type of a form your sample is, whether it is a crosslink, uncrosslink. Okay. There are different types of to accommodate different geometries and different state of the material, you can do it. But most interestingly, okay, when you see the onset of transitions, okay, you see, if I go back and show you out there also, it is here afterwards, you see in the onset there is a certain change in modulus. Okay. So, that onset you can mark, just draw two tangents and try to see the point out here, corresponding temperature. Loss modulus, you see it goes through a maxima, so corresponding to that also you get a temperature. And you get a maximum in tan delta, which is nothing but E double prime by E prime, that also gives you a signature. Now, question is that which one you should take it as a, that is a puzzle, which one you should take it as a TG of it. More conventional is taking tan delta peak as a TG of it. Okay. But again it depends on the perspective from which you are trying to analyze. Okay. See, many cases for a particular product, this lowest temperature offshoot in the modulus, it can be considered as a failure of that product. Okay. So, that gives you more precise, I mean that will be more appropriate from that point of view. Okay. But in the loss state, when the loss is maximum, okay, the physical property changes attributed to glass transition of the plastics. So, it is many cases it is considered for that. Okay. And it reflects the molecular process in more precise way. Okay. Now, obviously, do these two things, first you are getting at a very lowest temperature E prime onset, followed by E double prime onset and followed by that tan delta. Okay. So, what it represent? It occurs obviously at higher temperature. Okay. So, it is a good measure of rather like midpoint between the glassy and rubbery state. Okay. But technically speaking, if really you have to go for what is the glass transition, you have to do really in y x axis part of it, again if it is a storage modulus or loss modulus, the other side is a temperature. So, obviously, you are doing some temperature ramping. Okay. That is what you call it a heating rate. Okay. Then x degree centigrade per minute. Okay. So, if you reduce, make it very small and interpolate it to this rate, this is the rate degree centigrade per minute to 0, then you get the glass transition from there. So, of course, from DMA analysis you get many cases at a specific heating rate, I mean to DMA vice DSC, in DMA you may get a higher glass transition temperature. Okay. But it is again not absolute. So, this is what I already exemplified. Okay. So, it is a particular polysialic acid polymer, for as an example it is amorphous polymer, and here I already exemplified it. Okay. And is the, when you represent, this is the heating rate. Okay. Okay. This is the frequency of epsilon equals to epsilon 0 sin omega t. What is the omega value of it? That it reflects 1 hertz. Okay. And amplitude, this epsilon 0 part of it. Okay. So, this is what it is defined. So, what you do, as I mentioned it to do DMA experiment in the LVR, first you do the amplitude sweep, try to see the linear zone, middle of it, try to pick choose, okay. And then at a very low frequency of experiment, you try to do at a low heating rate, try to do your experiment, okay, if you are very much concerned with the glass transition and other secondary transitions in the polymer that may involve. So, let us quickly try to see what we can do using the this DMA. Fox equation I already talked about. If you have two component blends, the resultant Tg you can get it from these combinations. Okay. When it is of course immiscible polymer, then individual Tg will appear, otherwise it is going to give you a single Tg. Typically alternate polymer and miscible polymers, you try to get alternate copolymer or block copolymer, obviously you get 2 Tg, as I mentioned it to you earlier. Okay. So, polymer A, polymer B, you get a miscible blend. So, you get a single Tg. But if it is not, they will phase separate. So, both the polymer will show their signatures, 2 Tgs. Now, depending on how much is the interaction, suppose if you try to make it more compatibilized, more miscible, you try to. So, what will be, how it will be reflected? Tg will try to come closer. One is having a low Tg, another is having high Tg. You have a compatibilizer, they will try to come close. And if it is fully compatible, fully miscible, you end up having a 1 Tg. Okay. So, not only that, to what extent two polymers? Suppose if one polymer I am making it more and more polar compared to the others. Okay. So, maybe my phase separation is polarity dependent. Okay, it's enthalpy of it. Okay. So, at some point of time we will try to figure out what is the interaction, and that interaction is related to enthalpy of mixing. So, that way you can calculate out enthalpy of mixing of the sample as well. See, this is what the exemplify: polymer A, polymer B, we mix it. Had it been a purely miscible blend, we get in between that based on the Fox equation somewhere midpoint Tg, otherwise we get 2 Tgs. Okay. You can monitor either, as I mentioned, it is up to you or perspective, either you monitor storage modulus or loss modulus or tangential delta part of it, and we will try to see that. Okay, that shift. Crosslink density, of course, what crosslink density does, if you increase the crosslink density, you are trying to restrict the movements. So, as a matter of fact, okay, more and more crosslink will try to increase the Tg. Tg shifts to higher temperature at a given heating rate. Okay. But many a times you make a highly crosslink polymer, you get a very broad sort of a Tg of it. Okay. That is what it happens always. So, that this is the, if you plot log modulus part of it, you see if you gradually increase, okay, the crosslink density Tg is increasing. Okay. But at some point of time this plateau part will be vanished actually. It will try to show you like a highly rigid polymer looks like, or rigid material looks like. So, your plateau is essentially varies. You see, initially you have a viscous part of it, flow part of it, and that once you put the crosslink, it is gone. Okay. And this plateau got extended, but if you start putting more and more crosslink, the modulus is going high, and Tg also will be very much broad in there. So, effect of temperature on viscoelasticity, that means either way you can take it into consideration storage and loss part of it, or storage or tangent delta part of it, all the way same. This is essentially a ratio. Okay. So, if you try to monitor the viscoelastic behavior of polymer, means that there is often a time dependence of their properties in addition to any temperature effects. Okay. Temperature effect is of course there. An example is shown here. You see, with different frequencies, it is trying to shift. Higher the frequencies, Tg is going to be high, apparent Tg, I will say apparently, that transition maximum corresponding to transition is getting towards a higher temperature side. Okay. This will exemplify when one of the classes will talk about the rate dependent process. Let us try to quickly see some of the case studies where we can apply, other than the polymer blends as I exemplified. Of course, IPN also you can do the similar studies. Okay. So, many parts when it talks about interaction between two polymers, interaction between polymer and filler, interaction between the different additives in the polymer system, its aggregation, disaggregation, those will be reflective in DMA analysis in general. But still then let us try to look into carbon silica dual phase filler case. Okay. So, it says a carbon silica dual phase filler, let us try to tell me the background of it. It's like a silica is a filler for rubber, it's a good, it gives you good magic triangle attributes. Carbon black is very good, it has the thermal conductivity, it has the electrical conductivity, it mixes with rubber well. So, now if you try to have a hybrid behavior in a single filler, one point of time that became a hive basically, okay. It is a dual phase filler, carbon and silica. Okay. So, that particular system they have chosen for a chlorinated butyl rubber basically in this case. Let us try to see. So, here they loaded with that particular filler at different pHR of loading and try to monitor how the viscoelastic properties are changing. Okay. So, in general increasing amount of filler in the vulcanizer has no significant effect on the temperature of location of tan delta max, whatever maximum with respect to tan delta you are getting that. Okay. And all samples show Tg between -90 to -34 degrees centigrade. Okay. And in rubbery region, the curve of different vulcanizers crosses over around a wider temperature interval and due to the relaxation of interval. So, once you are adding a third component, say filler into the system. Okay. So, what will happen? You have a transition relaxation in the segmental motion, as well as there will be some filler aggregate formation, reformation will be reflected. Mind that although it is going to appear as a very small attributes, but ultimately essentially your primary transition may get broadened. Okay. So, that is very interesting, I am not going into that details part of it here. Okay. So, you can actually segment it at different temperature regimes. What is happening because of the hydrodynamic effect, because of the reinforcement effect, because of the filler it is absorbing or restricting some part of the chain. If it is of course restrained, then Tg apparent Tg will go high, okay, and that will show you signature of reinforcement. So, this particular things you can see the gross behavior of storage modulus as a function of temperature is changed a bit. Okay. So, with as you keep loading it, obviously modulus is going to get high, but of course, so in the plateau region is a different behavior it is appearing. It is because of the gross aggregation, gross reinforcement, okay, in that area. Remember, in the rubbery plateau regime, you have a segmental motion all throughout the chain involving large number of segments basically. So, you have a first place filler into the system that will restrain, and if it aggregates, again aggregate deaggregates. Okay. The filler rubber surface slippage, which generally for large strain you call Smolin's effect, that may also add up. So, that is how you can actually indirectly talk about what is happening there inside that in the family of rubber and filler in general. So, that is what it is elucidated here, those information you can fetch in. Okay. So, similarly, okay. So, other things for this particular paper is actually summarized here. Okay. Where is the micro Brownian motion, where is the filler aggregate breakdown, etc., etc., conformational changes that is happening. Okay. Another very important experiment you can often do, it is a strain dependent dynamic properties, particularly field system. Okay. So, if you try to monitor, so far we have been talking about storage modulus as a function of frequency or time or temperature. So, you just try to change the dynamic strain amplitude, okay, and try to monitor at a constant temperature and frequency. Okay. So, what will happen, that means you are trying to increase the amplitude part of it. Okay. Now, this filler, if it at all getting first it is getting dispersed, but if it aggregates, the very first strain you are putting, deformation you are putting, that will be due to the filler aggregates, because you are not first of all in a given composite material, if it is highly aggregated. Okay. These are the filler representation. So, you apply strain, before the polymer gets strained, the first place it will go to the aggregates. Okay. So, aggregate will break down. So, as a result, as a matter of fact, you will try to see that modulus which was initially very high at low amplitude, okay, it will try to diminish, and then it goes, the load obviously transfers to the rubber matrix. Okay. So, this delta T, this is the modulus initially, this T is a reflection of the initial breakdown. In fact, if you try to see the composite modulus, initially I can draw it here, initially the first part, if is the total strain, initially because of the rubber component of it. Okay. Then you put any filler, it will be hydrodynamic component of it. Okay. Then you have a rubber filler interaction part of it. Those at a small amplitude they will not break down. Okay. Then what is the aggregate part of it? It actually breaks down from this is the due to the aggregate filler interaction part of it. So, what you can measure, how much is the filler interaction in the polymer. Okay. So, that ultimately gives you a signature up to which percolation limit of filler you must add. Otherwise, afterwards you may have gross deterioration of some of the properties of course. So, this DMA enables you to grossly understand what is happening there in terms of filler aggregation into the matrix. So, same thing you can plot tangent delta. So, initially which is small in amount, okay. As you keep gradually increasing the filler content, this tangent delta, the breakdown is more severe, more and more severe, and that will reflect grossly in the tangent delta part of it. Okay. And of course, so as I mentioned it to you, the LV, you have to consider one thing, LVR also gradually as you keep filling the polymer matrix with the rubber, it will try to reduce. So, it becomes grossly nonlinear in behavior. So, I am not going into that contribution. So, what actually you can understand polymer filler interaction by amplitude sweep, filler interaction, disruption and resorption of the hybrid rubber cell, which is actually covering the filler aggregate, and of course, I mean for a pure system, pure crosslink system also you can extend that studies and to understand breaking and deformation of crosslink, particularly if it is a reversible crosslink self fillable material, you can extend your studies. So, that is another perspective here. So, again carbon black, which is a classical filler in the same chlorobutyl system. Okay. So, here also you can see the loss tangent is monitored as a function of temperature. Okay. So, below Tg tan delta increases with the decreasing surface area. Here the study is being done with a different particle size. Okay. ISF, HAF, okay. SRF have two types, one is having high structure, another is low structure. MT and GPF, which are a much larger size, but in general what is happening below Tg tangent delta decreases with decreasing surface area of the filler, but of course, at a similar loading if I consider the Pine effect. Okay. So, smaller the size it will try to aggregate more. Okay. It has a more volume surface to volume ratio in that essence. Okay. So, that way you can see different rubber field system at a particular pH level. So, you can see gross tangent delta behavior across the range of temperature encompassing the Tg original Tg of the system. See here the Tg maximum Tg is most diminished, I mean its peak of it, okay, for the most field system, because field system will try to occupy more volume. So, effectively the volume fraction of the rubber decreases in the system. Okay. So, that is how you see the gross effect of it. Okay. So, similarly this table gives you a comparison. Okay. Although there is a very small little shift in terms of Tg if you consider, okay, from a very small nano size filler to the very large close to the micron size filler, you see minus 28 to 32 degree. 32 of course, will be smaller the size, it will try to restrain, it will immobilize the polymer chain. The peak magnitude of course will follow the reverse order. Okay. So, that is how it goes. Similarly, so as I mentioned, in line with the CSDP carbon silica dual field system, similarly you will see the reflection in terms of storage modulus part of it. And if you consider the effect of temperature for the same system in the loss modulus, you can see, I mean obviously you know how to explain it by now. Okay. I am not going into the details part of it. Again, Pine effect you can monitor across different temperature. I mean it all depends on the temperature of applications. Okay. And what is the amplitude part of it is really involved. So, this experiment Pine effect not only at a fixed temperature you can do the experiment at low temperature. Okay. And you can do it still higher temperature, room temperature, you can go still higher temperature like 70 degrees centigrade, and that you try to explain from the point of view of filler aggregation, softening, slippage, etc. etc. So, that is how you can use it. So, before we really go into that, okay, the methodology processes are highly depicted in different standard. So, these are the ISO standard, the general principle is elaborated here, then torsional pendulum, different DMA that I did not talk about is given, shear vibration mode, torsional vibration mode, longitudinal and tensile vibration mode, how you do it. Okay. So, these are some of the references. Of course, the first book is very good if you try to understand the viscoelasticity, although in this particular course I have a very limited scope, but of course, in the next semester we are going to talk viscoelasticity and rheology in more details. Okay. And Ferry's book is the most like a Bible. Okay. There are many other books which you can consider, and DMA, of course, there are many open literatures also you can get it. So, let us try to quickly conclude. We covered the basic conception of viscoelasticity in reference of course, resilience, the working principle of DMA and with common geometries. Okay. And then we talk about response of classical extremes and oscillatory test, storage modulus, loss modulus, tan delta, these three parameters, a typical plot of DMA, TG determination, okay, in the point of view of blend system, okay, effects of cross-linking, effect of temperature and viscoelasticity, just a field system, two field system, the case studies we have made. There are several ways you can apply it, all depends on your perspective, and of course, the standard names I have uttered you. With that, thank you very much.